Hello everyone, and now we are going to start with the next chemical parameter, which is alkalinity and hardness. So in this lecture, we'll be discussing in detail what's alkalinity and how to measure it, and how to remove it, and what's the hardness, how to measure it, what is the importance of these terms. So we'll be discussing all these today. So let's start. So now we have the very first question, which is what's alkalinity? So alkalinity is the capacity of water to neutralize the acids. What does that mean? So it's saying to neutralize the acid. So it means that whatever acid is present. So from our basic chemistry, we know that acids are uh, present due to H plus ions, right? So H plus ions create acids. Now, if anyhow we try to neutralize this H plus ion, then we'll be having a neutral water, right? If water is having a lot of H plus ions, we'll be calling it as acidic. So it's acidic, in acidic range. So in our previous lecture, we studied about pH, right? And pH was nothing but it was minus log of H plus ion concentrations, right? So H plus ions gives acid, so it has acidic property. Now if I add something, for example, if I add OH to H plus, OH minus, it will create H2O, and which becomes neutral, right? Right. So OH minus is what which is neutralizing H plus. So we call OH is an alkaline ion. So it works as alkaline ion. That's why it's neutralizing the acid. So as alkalinity is nothing but it is the acid neutralizing capacity of water. So the ions which get combined with H plus and neutralize it to become a neutral molecule, and then we call that those ions are alkaline ions, and the alkalinity is the property by which this is getting neutralized. So this is what alkalinity is. Now, so the conceptual understanding here, so the pH is the current condition, and alkalinity is the resistance to change that. So that means the if the pH is 8 point something, 8.5, and if I'm starting to add more and more acid, so I told you, right, I told you the water is always in the range of 6.5 to 8.5 of pH, neutral, like it is natural water pH. So the water has the capacity, whatever you add in that, so at um, like for some extent water tries to make its pH only between 6.5 to 8.5. For example, if you add a bit acid, so it just works something like that, that the pH after adding acid also should not will not be falling below 6.5. Up to some extent it will try to neutralize that, and even if you add base, then also the pH will not increase after that, after 8.5, up to some extent. Like if you are adding a large amount of acid or base, it will definitely increase, but for some extent the natural water tries to keep its pH between 6.5 to 8.5. See, you what you see, you are dumping the industrial waste into the water, into the river water, but after some time you see that the river pH is has become, for some time it will be a 4.5 or something, between the lesser range into the acidic range, but after some time the pH will become into the range of 6.5 to 8.5. So how the water is doing that? That's another case. It has its carbonate system it's working there. We'll not go into that deep into this, but we have to see that alkalinity is the resistance to change of the neutral water. So this is what we wanted to understand. Now we have sources of alkalinity. So alkalinity comes from mostly it comes from atmosphere. And now how it is coming from atmosphere? So we have so much of CO2 in atmosphere, and most of the people think, yeah, CO2 is acid, right? Because when CO2 is mixed with H2O, it will create carbonic acid, H2CO3. It's what? It's carbonic acid. Then it's acid. But how it is creating alkalinity? So it will not remain into this carbonic acid form into water, because this carbonic acid will be for pH lesser than 6.3, I can say. For lesser pH of 6.3, carbonic acid will be there. But water has pH of around 6.5 to 8.5, right? So in this range, this carbonic acid breaks down. It gets converted to H plus HCO3 minus. So now you see there is a negative ion, it will create alkalinity. We call it bicarbonate ion. So it's a bicarbonate ion. It will create alkalinity. Alkalinity are all like always created by a negative ion. Acid is always created by a positive H plus ion basically. Now this also doesn't stay further. This HCO3 minus also gets decomposed, dissociate we will say, also get dissociates into H plus CO3 2 minus. Now the CO3 2 minus is called carbonate ion. This is also a region to create alkalinity. And at the very first we have water itself. Water can also get broken into H plus and OH minus ion, and this H plus is acid and this OH minus again negative ion, and we call it as hydroxyl ion. This will also create alkalinity. So we have bicarbonate, carbonate and hydroxyl ion. So these three things create alkalinity in a large extent. There are other things which create alkalinity, but but the effect of those are very small. But because CO2 is in a larger, in a higher extent into the atmosphere, due to this the alkalinity, and even the water pH is designed something like this, that it stays in between the favorable condition for bicarbonate and carbonate ions. So alkalinity due to carbonate and bicarbonate is also a major one, and hydroxyl ion is already there into the water molecule, so this is also a major one. So due to these three, alkalinity exists, right? And then we have other ions. For example, we have uh, BOH4, we have NS minus. So we have so many ions, like we have H2PO4, H2PO4 minus, HPO4 minus, 2 minus. So these are the ions. These are also creating alkalinity. Basically all the negative ions, and this is also because there is hydroxyl there. So, but we will not be going into detail of these. Only the three things are the important ones. So now we have, by this we have the types of alkalinity. So we have hydroxide, we also call it as caustic alkalinity. And then we have carbonate alkalinity, CO3 2 minus. will this is alkalinity, and then we have bicarbonate alkalinity due to SCO3 minus. So there are three types of alkalinities that we have to keep in our mind. So these are alkalinities. Now, what is the importance of alkalinity? So because water has amount of SCO3 minus and CO carbonate, this is called buffering capacity. So the property of water that I am saying, that it keeps its pH from 6.5 to 8.5 range only. This property is known as buffering. So this is known as buffering. So this buffering capacity comes due to the alkalinity. Alright. So because there are carbonate and bicarbonate ions present there, and then it prevents sudden pH change, alkalinity, right? Whatever you are going to add, pH will not suddenly drop from 6.5 to less or 8.5 to higher one. And it's very important to the water treatment. You will see when we'll be studying water treatment, we'll be discussing that also. So this is what the alkalinity is important for. Now we have measurement of alkalinity. So the alkalinity can be measured by the titration method. So one thing we can like simply measure it by pH meter. We will check the pH and we can say it's alkaline side or not. So that's pH meter. And in the lab, how we do it? We titrate it with HCl. And then the indicators which we'll be using is phenolphthalein and methyl orange. So titration with HCl, how does it work? So if water is having alkalinity, so the alkalinity, the pH range for alkalinity is 7 to 14, right? If the water pH is 7 to 14, we'll be saying that it is in alkaline side. Now, so alkalinity is present due to OH minus, HCO3 minus and carbonate ions. Due to this, alkalinity is present, right? Now, titration, if I am doing titration, so the caustic alkalinity is for greater than pH, we'll say 12. Bicarbonate alkalinity is for around pH greater than 10. Basically it is 10.5, 10.3 something, and for the range of pH 8.5 to 10, it's carbonate alkalinity, and for pH lesser than 8.5 or 8, we have bicarbonate alkalinity. Okay. Now, very first thing, the if we are adding, so the pH is let's say the pH is in the range of greater than 10. pH is in the range of greater than 10, and we have burette. In the burette, we'll be adding HCl. So HCl is here, and we have taken in the conical flask are this alkaline water, and we will be adding drop of phenolphthalein indicator. So if phenolphthalein, so the phenolphthalein indicator works best. So the color change reaches at the pH 8.3 for phenolphthalein. So for pH greater than 8.3, it's pink in color. And when pH becomes exactly 8.3 or less than 8.3, it changes its color from pink to colorless. And then we come to methyl orange. Methyl orange, it changes its color at pH 4.5 from yellow to orange. Orange is red, I can say. Now, what we are doing, so the water is having greater than 10 pH. That means if I am adding phenolphthalein indicator, so the color will become pink here, right? And now I am dropping HCl drop by drop. So what HCl is giving? It's giving H plus plus Cl minus, right? Now this H plus will first neutralize OH minus because pH is greater than 10. So the H plus will be neutralizing OH minus and it will be giving H2O, right? Once all the OH is consumed, this H plus will then neutralize CO3 2 minus because the pH is in the range of 8.5 to 10. Now, this OH, this H plus will start neutralizing CO3 2 minus and it will be giving SCO3 minus. Okay, and after that the fully CO3 2 minus is neutralized. Now this H plus will start neutralizing SCO3 minus. Uh, yeah, and see, carbonate neutralization will happen, and then the pH, the color, when the pH of the water drops to 8.3, the color will suddenly become to colorless, right? So it will suddenly become to colorless. Now at this point we will be adding, now in this it has become pink to colorless, this colorless. Now I wanted to check what is SCO3 minus alkalinity, right, where the total alkalinity will end. That means full SCO3 will be converted into H2CO3, that means carbonic acid. So when the SCO3 minus is also fully neutralized, then only we can say that yeah, the alkalinity is fully recovered due to the HCl that we are adding. So phenolphthalein indicator's work is done because pH 8.3 is reached. Now we'll be adding a drop of methyl orange, and we'll be seeing the color of the solution will be something reddish orange now. And now I'll be adding more HCl. When methyl orange uh, endpoint will be reaching, we'll be having from this the color will be yellow. Okay, so the methyl orange endpoint, after it will reach, the color will become yellow, and at this point I can say that full SCO3 minus is also neutralized to H2CO3, that means carbonic acid. So now fully alkalinity is neutralized and we have done the titration with HCl, and we have uh, calculated. So yeah, and the thing that we will be keeping in our mind is what time the color from pink to change to colorless, that time we'll be noting. So and what was the volume, like if the water if the HCl was at this and it reaches to this, so we'll be noting the volume, right? And we'll be calling this as phenolphthalein alkalinity. So the first thing that will be reached, we'll be calling this as phenolphthalein alkalinity or P-Alkalinity. Okay, and then the volume it will take up to the methyl orange endpoint V1 we can say, and V2 we can say, and that we'll be calling methyl orange alkalinity. Okay, these two will be adding and in combination will give the total alkalinity, right? So total alkalinity is nothing but phenolphthalein alkalinity plus methyl orange alkalinity. Now how will we, I have the volume for the titration. So how do we calculate the phenolphthalein alkalinity? For phenolphthalein alkalinity, so in this, let's say we added V amount of the sample, alright, and the acid HCl is of N normal. So N normal HCl we used. So phenolphthalein alkalinity as CaCO3 can be given by N into V1 upon V. V is the volume of sample that we took into 50,000. So we will be getting it into milligram per liter. So this is the phenolphthalein alkalinity. And similarly, if I want to calculate methyl orange alkalinity as CaCO3 equivalent, so N is the normality of acid, V2 was the volume it was used for methyl orange, P is the total volume of the sample into 50,000 to convert it into milligram per liter as CaCO3 as CaCO3. So this is how we calculate the alkalinity, and let's say the P-alkalinity is A and MO alkalinity is B. Let's simply denote it like this. Now I'll be just telling you the table, and we'll be knowing the alkalinity, different kinds of alkalinity with that. So for example, I have if in case I have A is equal to B, that means it's the first case. I have A equal to B. That means I'll be having phenolphthalein alkalinity equal to the methyl orange alkalinity, right? And that means the volume it took for neutralizing the phenolphthalein alkalinity, the similar it took for it took to neutralize methyl orange alkalinity. So here in this case I can say caustic alkalinity is 0, and we have bicarbonate alkalinity also 0. That means SCO3 minus alkalinity is also 0, and carbonate alkalinity as 2 times of A, and total alkalinity is also 2 times of A. Okay, and the pH range is between, initial pH was approximately 10.5. So A had become equal to B. This is the first case where A is equal to B. Methyl orange alkalinity is equal to the you have phenolphthalein alkalinity. Now the next case which comes to us is A greater than B. Okay, so if A is greater than B, that means caustic alkalinity, that means OH minus alkalinity. I'm not writing alkalinity, you just simply understand it by your thing. So that is A minus B. Carbonate alkalinity is 2 times of B. Bicarbonate alkalinity is 0. We have total alkalinity, that is A plus B, and the pH was in the range greater than 10.5. Okay, and the third case when A is less than B, that is we have OH minus alkalinity, that is 0. We have carbonate alkalinity CO3 minus, which is 2 times of A. We have SCO3 alkalinity, which is B minus A, and we have total alkalinity, which is A plus B, and the pH comes into the range of 8.3 to 10.5. Okay, and fourth case I can say if A is greater than B and B is equal to 0, that means methyl orange indicator didn't work. We didn't have to take the volume of methyl orange titration, only phenolphthalein titration worked here. So in this case caustic alkalinity is there, that means OH minus alkalinity is A, and we have carbonate alkalinity CO3 minus as 0, and we have bicarbonate also 0. Total alkalinity is A, and the pH in this case is also in the range of greater than 10.5. So this case A is greater than B, and this case A is greater than 0 and B is equal to 0. So B, when B was there, that means little bit of acid was there to neutralize the carbonates, bicarbonates. That means methyl orange indicator was methyl orange alkalinity was present, and if that was present, we would be having carbonate and bicarbonate alkalinity there. But in the fourth case, I can see there was no methyl orange alkalinity present. That means we were not having any carbonate or bicarbonates in there. If that were there, we needed to have methyl orange alkalinity so that SCO3 minus can be neutralized to carbonic acid. But that was not the case here. Only we got the phenolphthalein in alkalinity. So what we can say from here, only OH minus, that means caustic alkalinity was present, and that was equal to A only, and the total alkalinity will become A. So these are the cases that we should remember in terms of calculating the alkalinity. Now I have some basic things that we should know to calculate alkalinity and to do any numerical before that. For example, so the basic terms that will come, let me have new slide for us. So the basic things that mostly that we'll be having is the molecular weights, right? So just now I wrote as CaCO3, equivalent of CaCO3. So what's that? So we need to understand these terms also, so that we can do the numericals properly, right? So let's see, what's that? Not now. Yeah. So we have things like, yeah. So alkalinity is measured by titration, right? And some molecular weights are very important, and we should know that. So molecular weights of some molecules, for example, we have CaCO3. So what is the molecular weight? Calcium is 40, right? And carbon is 12, and 16 into 3. So we get it as 100 molecular weight. So it's 100 grams. And then we have similarly H2SO4. This also will be in our use. So H2SO4 has the H is 2 into 1, and then sulfur is 32, and then we have 16 into 4, and then we get its weight as 98 grams. And similarly, we have seen bicarbonate. So bicarbonate is 1 plus 12 plus 3 into 16. So its weight is 61 grams. And then we come as carbonate. Okay. So CO3, 2 minus 12 into, so 12 into 16 into 3, 12 plus 16 into 3, we get it as 60 grams, right? And we'll be seeing OH minus, so it's 16 plus 1, that's 17 grams, and there is another one, we call it as HO4 minus, so 32 plus 4 into 16, it's 96 grams. All right. So these are some of the important molecular weights that will be coming into the importance of numericals of doing alkalinity and as well as the hardness. Okay. Now, if I want to calculate these are the molecular weights. Now, if I want to calculate the number of moles into the system, so number of moles is nothing but given weight upon molecular weight. Okay, so this is what number of moles is, given weight upon molecular weight. So for example, if I have to calculate 300 kg of calcium carbonate, CaCO3. So what is the number of moles in this? So I can say, so the given weight is 300 kg. Molecular weight is in grams, so I need to change it into grams. So this is 300 into 10 to the power 3 grams, and the molecular weight is 100, right? So it's nothing but 3000 is the equivalent moles. So 3000, right? So this is how the number of moles is calculated, and you have the molecular weight here, and yeah. Now let's have another slide. Another blank. Let me add another blank, and let me add another blank. Yeah. Now, if I want to see what is equivalent weight, equivalent weight. So these are very important terms. You should understand how to calculate those, and these will be so see, molecular weight is different than equivalent weight. You can't get confused, so you should know these. So it's nothing but it is weight of 1 gram equivalent. Alright, so equivalent weight, if I want to calculate equivalent weight, it's nothing but you have molecular weight and then you will be dividing it by valency. Valency is nothing but the charge upon them. So if I want to calculate the equivalent weight of CaCO3, so it's nothing but molecular weight is 100 and the valency, if I break it, so the valency it's -2 plus 2. So that valency is 2. So it's 50 gram. Equivalent weight is 50 grams. Right? So this is what equivalent weight is. So if I want to calculate what is the uh, uh, number of gram equivalents. So number of gram equivalents. So it's nothing but number of gram equivalents is given weight divided by equivalent weight. Alright. So for example, if I have to calculate the weight of number of gram equivalent, example, we have to calculate number of gram equivalent of 300 milligram of CaCO3. Okay, so the given weight is 300 milligram. I'll be changing it into grams, so into 10 to the power -3 divided by, I'll be dividing it by equivalent weight. So equivalent weight of CaCO3 is 50, right? So this has become 6 into 10 to the power -3 is the number of gram equivalents. Alright, so these are the different terms that come into the picture when we are doing the numericals for alkalinity, even for hardness. This will come, right? Now, there are some more basic terms which are yeah. So the one of the basic terms is normality. Now what is normality? It's number of gram equivalents, okay, divided by in a liter. So it's normality. So number of gram equivalents per liter, it's normality. And then we come to the term molarity. So molarity is nothing but number of moles, okay, per liter. It will be denoted as M. Okay, so normality formula is number of gram equivalents. Molarity formula is number of moles in a liter. All right. So for this, let's have one example. So we have example let's say we have 2 liters of water, okay, and in this I added 196 grams of H2SO4. All right. Now can I calculate the concentration of H2SO4? So it's nothing but concentration is what? Concentration is in gram per liter or milligram per liter. So the concentration is 196 grams in 2 liters. So it will be 98 gram per liter. So in 1 liter of water there are 98 grams of H2SO4 molecules, right? So this is the concentration. So I have the concentration now. So with this, the first thing that I want to calculate is moles. And now what is mole? Mole is given weight upon molecular weight, right? So the given weight is 196, right? What is the molecular weight? Molecular weight for H2SO4 I just calculated, that was 98. So the number of moles which are present is 2 moles in 196, but the concentration in moles per liter is moles per liter, the concentration. So this is the number of moles, right? Number of moles. So number of moles is nothing but given weight upon molecular weight, 196 upon 98, and that comes to be 2. Now moles per liter is the concentration. So first way to denote concentration is gram per liter, and we can also denote it in moles per liter. So there are 2 moles in 2 liter. So the concentration in moles per liter is 1 mole per liter. So this is another term of saying the concentration. And now let's calculate the gram equivalent. So how will I calculate the gram equivalent? So gram equivalent formula was given weight upon the equivalent weight. So the given weight was 196 grams and equivalent weight is nothing but 49 grams. So this will be gram equivalent, and in terms of per liter we have to calculate, okay, because we are calculating concentration in the terms of concentration. So for per liter it will be 1/2. So it comes to be as 2 gram equivalent per liter. Alright, so this is how we calculate the gram equivalent. Now if I want to calculate the molarity. So for molarity the formula was number of moles per liter. So the number of moles is 2, right? We just calculated 2. But in how many liters? 2 liters. So per liter is 1 mole per liter. So the molarity is 1 mH2SO4. This is molarity. Now if I want to calculate normality of this, so the normality is what? Number of gram equivalents per liter. So what are the number of gram equivalents we calculated? So that was nothing but 196 weight upon molecular weight 49 and equivalent weight. So that is 98 upon 2 because it was H2SO4, and it is for per liter, right? So for per liter that means divided by 2 because there is 2 liters. So it's 4 upon 2, that is 2 normal H2SO4. That means if 1 molar H2SO4, that means it's 2 normal H2SO4. So can I say, so for example, if we have 20 normal H2SO4, then we'll be having 10, this is similar to 10 molar H2SO4. Okay, and for this we can say the relationship between normality and molarity, in this case it's coming to be that normality is 2 times of molarity, right? This is for the valency too. So if we have, in general I want to write, so normality is nothing but valency into molarity. So this is general relation. So that means if I have HCl, so for that one normal HCl is equal to 1 molar HCl because the valency is 1. So this is how we calculate the basic gram equivalence, normality, molarity. So these are the basic terms, right? So let's see one numerical. So in this we have been given, I need to calculate the alkalinity. Alright, so the equivalents are given. So that means we have given the weights of uh, different ions present into the water. So there is 420 grams of CO3 2 minus present into the water, and then we have 244 grams of SCO3 minus into the water, and we have 68 grams of OH minus into the water, right? And we have to calculate the alkalinity as CaCO3 equivalent. Okay, so there is one thing that I wanted to tell you. I didn't tell the full formula of alkalinity. So the alkalinity formula, say if I want to calculate the total alkalinity, how, in terms of these type of questions, when the volume of titration will be given, we'll be using the volume formula and the table that I created, and when it is given into the gram equivalent or grams, the weight of each and every ion, we'll be doing it by this. So the total alkalinity is nothing but its gram equivalent of, or the moles of OH minus, and plus we have uh, HCO3 minus plus CO3 2 minus, and we'll be doing minus of H plus ion. So this gives the total alkalinity in gram equivalent, right? So it will be given in gram equivalent, and then as CaCO3 or something we have to do, we'll be multiplying it by the equivalent weight of CaCO3. So for example, here we have, 420 grams of CO3. Can I calculate the gram equivalent of CO3 2 minus? So it's nothing but weight upon equivalent weight. So 420, the equivalent weight of CO3 is 30, 60 upon 2. So it comes to be 14, right? And if I want to calculate gram equivalent of HCO3 minus, and HCO3 is 244 divided by 61, it comes as 4. And if I want to calculate gram equivalent of OH minus ions, so it's nothing but 68 divided by the molecular weight of OH is 17, right? So it comes to be as 4. And I also need H plus ions concentration, right? So I have the relation that H plus ions into OH minus ions is 10 to the power minus 14, right? Can I calculate H plus ion? Can I calculate OH minus ion concentration? So that is nothing but 68 gram equivalents. We'll be multiplying by gram equivalents directly. So I can get 10 to the power minus 14 upon 68 upon 17. So the H plus ions is 10 to the power minus 0.25 into 10 to the power minus 14. So this is the concentration of H plus ions. Okay. Now, and this is in gram equivalent. This is gram equivalent. And these are also gram equivalents. Now, can I calculate the total alkalinity? So total alkalinity is nothing but OH minus ions. So that is 4 plus SCO3 minus ions 4 plus 14 minus 0.25 into 10 to the power minus 14, and we have to calculate it as CaCO3. So CaCO3 equivalent I have to multiply 50. So, and one more thing, if I want to it will come into grams per liter. So, but the concentrations are very low, so I need to, let's convert into milligram per liter. So it's milligram per liter. So this comes as 14 plus 4, 18 plus 4, 22 minus 0.25 into 10 to the power minus 14. Do you understand? The number is very small. So can I simply say 22 into 50 into 10 to the power 3? So it's 11 into 10 to the power 5 milligrams per liter. So this is the alkalinity. So this is how we calculate alkalinity, and I think this lecture is becoming very big. So I almost took an hour or quarter of an hour to explain alkalinity. It was a very big topic indeed. So I guess you guys understood, and the different type of questions that come to alkalinity, being it for titration, be it with this calculation purpose of we'll be giving grams of each and everything and we'll be calculating the alkalinity. So this is how the things are working, and hardness I need to do in the next lecture. So let's meet into that. Thank you.